Thanks for the intro, Jeff. Hello, welcome all to the research stage here at CogX. This is a session on neuromorphic computing, the next computing revolution. That's something we will be discussing. My name is Luke Fleet, and I'm the physics and technology editor for the journal Nature. Before introducing the session, I'd just like to start by saying that Nature stands in solidarity with those that are fighting to try to create a just, equitable, and inclusive society. We're supporting the Black Lives Matter movement and the strike for Black Lives, and we will not be publishing our issue today or our podcast, and we have stopped most of our day-to-day activities as we try to reflect and think about what action we can take to tackle systemic racism in academia and also within our own ecosystem. And I'm sorry that it's taken us so long to do this. Nature was invited to curate today's content for the research stage, and after some discussions, we have decided to continue with our participation in CogX. Our aim is to spotlight research that we think are some of the most exciting that we're seeing and showcasing in our journals, and to try to put that into context for you. In this session, we'll have three wonderful speakers, which I'll briefly introduce. Before doing so, I want to first state that the speakers are fully supportive of the movement, but have agreed to fulfill their commitment to the CogX organizers and to you, the participants. So the session will start with a presentation from Chiara Bartolozzi, a researcher from IIT in Geneva. She leads the Neuromorphic Systems and Interfaces group there, who are applying neuromorphic engineering approaches to robotics. And I'm sure that she's going to share with us some of the fascinating capabilities that they've developed for their iCub robot. After the presentation, we will bring in two other speakers for a panel discussion. One of those is Steve Furber, a professor of computer engineering from the University of Manchester. In the 1980s, he worked at Acorn Computers, where he was a principal designer of the ARM 32-bit RISC microprocessor. Over 130 billion variants of those have since been manufactured, powering much of the world's mobile and embedded computing. He now works on neural systems engineering, where the Spinnaker project, which I'm sure we'll hear more about, has delivered a computer that's optimized for brain modeling applications. And last but by no means least, we'll be joined by Huaqiang Wu from Tsinghua University in Beijing. He's the Deputy Director of the Institute of Microelectronics and also the Deputy Director of the Beijing Innovation Center for Future Chips. He spent a number of years in industry before returning to Tsinghua, which is where he graduated. And he's working on brain-inspired computing technologies and the hardware necessary for artificial general intelligence, which has been discussed in lots of sessions here at CogX. After this, just a reminder that we will have the breakout Q&A, which will start at 11 a.m. So please do have your questions ready and join us for that. I will try to get through some of your questions during this session, if possible. So please do send them in, but we'll have plenty of time to go through more during the Q&A. And for now, let's give a warm virtual welcome to Chiara. So Chiara, the stage is yours.
Hi, everybody, and thanks, Luke, for the nice introduction. It's really a pleasure and an honor to be here and have the duty to kind of introduce the topic of today, that is neuromorphic computing. So let me know when the slides are being shown. Okay, thank you. So the topic of today is neuromorphic computation. So what I thought is to start trying to tell you and discuss with you what computation is. So a general notion of computation is solving high-precision numerical problems. So if we want to compute a logarithm of a very big number, or if we want to solve an equation that comes from a problem of physics where we have things moving under forces and so on, or we want to solve a differential equation and many other numerical problems, then the computers, as we know them now, are the best solution. They can give us a very precise solution in a very short time. These computers are based on what is called the von Neumann architecture. So basically, if you look at the structure, we have a central processing unit, or a CPU, that does the computation, and we have a memory where the data are stored. So the central processing unit communicates continuously with the memory to retrieve data, do computation, and give us the result. So these architectures are perfect for such problems. And while, for example, we as humans are struggling with solving these complex mathematical problems. On the other side, we can say that another type of computation is what is needed to interact with the world. So understanding the world around, making sense of the sensory input that arrive from many different sources, and plan for actions. So here are very simple examples. In the animal world, an animal has to understand where a prey is, detect it in the scene, and plan very quickly for actions to do in order to survive. And in a very different environment, humans when driving have to detect pedestrians in a very complex environment and try not to hit them and drive safely. Bees have to find food in a very complex environment that keeps changing with the lighting of the day. They have to communicate to their mates where food is and organize their society. Another example is cooking together. You have to, find the ingredients, know where they are, open the shelf, take them, and then coordinate with your action with other players to achieve a goal. This is something that the von Neumann architecture has big problems in doing. The first big problem is understanding the sensory signals that are needed, that are the first step to being able to act in the world. Very recent advancements in the state of the art using deep learning techniques can partially solve some of these problems, but in a very brittle way that collapses when the environment around changes, because they cannot really adapt to changes of the environment and of changes of the people around us. And also, they can perform this computation at a very, very high cost. So this is not the right solution for this type of computation. And what some engineers started doing a few years ago was to start looking at how the brain solves the same problem, because brains evolved over many years to be perfect in achieving a task given the situation around. So the key idea of neuromorphic computation is understand the computational principles of brains. And this is kind of the flow. If you start from top left in this slide, you can see the imaging of neurons in the visual cortex of a cat. By studying how these neurons communicate and process information, we can derive computational principles. And that's the second figure that you see, the round circle that represents each small circle represents a neuron, and the arrows represents their connectivity. This is one of the computational principles that can be observed in the brain. And then we can derive a technology that implements these type of neural primitives, and at the end of the chain, we can try to implement these neural primitives on robotics, for example, to accomplish a task, to put this type of computation in action. So, which are the computational principles in the brain? Well, this is still a matter of research. It's really an interesting research topic, and there's a lot of researchers working on that. I can give you a very rough and not detailed glimpse of some of the important principles that have been observed. So what you see here are two neurons, two cells of the brain that communicate with each other. sending action potential that are transferred by the synapse to another neuron that does computation. So what can we observe in very high-level general terms? Well, first of all, neurons are redundant, they are slow and imprecise computing elements. They are much slower than a single transistor that we find as basic building block of a von Neumann architecture. But still they can do precise enough computation to let us survive in the world and do also amazing things. And this is technologically a very important thing, because while the technology is shrinking, the transistor elements, they become more and more unreliable. And therefore, the neuromorphic computing approach that exploits these redundant, slow, and imprecise computing elements that keep changing over time to do computation can be a technological solution. The other important aspect is that the computation done by the neurons is analog, and so different input sources are integrated in the neuron, but the communication of the information is still digital, so it's very robust to noise. Another very important difference with respect to von Neumann architectures is that memory and computation are co-localized. So you don't have a central processing unit that needs to exchange information with another memory unit, but everything is co-localized. And the memory is inside the synapse. So the synapse, depending on the activity of the neurons, can change its properties to change the communication between two neurons. And this is what forms the basic principle of memory. Then we have recurrent connectivity. The neurons connect to each other in very complex patterns, and this recurrent connectivity allows the neurons to compute looking at what happens to their neighbors. So the information is processed in a way that looks at the context of the information. And all this can be deployed in the world because there is adaptation and learning at multiple temporal scales. And this is very important when you want to deploy an artificial system in a world that is ever-changing. So everything can be summarized also in the fact that the neurons and the brain and the sensory systems encode the information in an efficient way. So which are the neuromorphic technologies that derived in the years following these observations? Well, the first is a different way to do sensing. Instead of taking snapshots or pictures of the external world, the neuromorphic sensors, they react to changes of the stimuli. So this is a video of a neuromorphic vision system where you see that when a person moves, it generates events that are very similar to action potentials from the neurons, and you have a stream of continuous information that is very important to be able to capture information from the external world. So this vision sensor was developed in Zurich at the Institute of Neuroinformatics and is now being developed by other companies and labs around the world and being used in robotic applications. Then the sensing research went to the technology of touch. So where here you see the tactile sensors of the iCab robot that you saw right at the beginning of the presentation. And here again, we can use neurons to send action potentials when there is a touch in the skin of the robot. So the robot can perceive a touch when it's been in contact with other agents in the environment, and then it's silent in the rest of the time when there's no tactile events. Then there's the auditory sensors inspired on the cochlea that again work very similarly to how the cochlea processes the auditory signals. Then the other big part of the developed neuromorphic technologies is for processing. Here I just put few examples of the many different neuromorphic processors that have been developed that I think are the ones that are mostly used by different research groups in the world. This is Spinnaker, and we have here Furber, who is the lead of the project that developed Spinnaker. We have the neuromorphic chips from the group of Giacomo and Diver in Zurich. There's now AI Cortex that is producing them. These two systems, they are kind of at the opposite ranges of the neuromorphic technologies. One is based on digital technology, very fast computation, but highly parallelized. The other one exploits the physics of transistors when used in subthreshold domain to perform very low power and parallel computing with spikes. And then there's two big players that started developing neuromorphic systems that are IBM with True North and Intel with Loihi. As I said, I missed many other processing systems like Braindrop and other ones that are being developed by other research institutes, but I think these are kind of the most representatives and the most used currently. So finally, to conclude, neuromorphic technologies have the potential to be applied and be game changers in very different applications. Here you see an example of what we can do with event-driven vision sensors, with neuromorphic vision sensors on the robot iCab. We can have tracking at few kilohertz. That's kind of impossible with a traditional camera, at least not at the same speed and not with the same amount of computation required. So it can be run on a single laptop. But there's many other different applications where neuromorphic computing can make a difference, and that is high-speed vision, biomedical signal processing, health monitoring, prosthetic devices, brain simulations, and adaptive systems in general. So I believe we will have time to go more in details of what are the neuromorphic technologies available, which are the pros and cons, and which are the promising applications of these in the Q&A and during the panel discussion. So with this, I conclude my presentation, and I thank all the people listening and the European project that had supported our research. Thank you.
Okay, Chiara, thank you for this wonderful introduction to computing, the brain, and neuromorphic technologies, and for showcasing some of the fabulous capabilities of the iCub robot and its impressive neuromorphic vision sensors. Steve, if you don't mind, I'd like to bring you in now, if that's okay.
Yeah.
As I mentioned in the introduction, you are obviously the principal designer of the ARM microprocessor and led the development of the Spinnaker architecture, which Chiara has just flagged. Could you maybe give us a little bit of an introduction to Spinnaker, explain how it differs from more conventional hardware architectures, and maybe comment on how the hardware landscape has evolved in recent years? Chiara just mentioned a few different chips, for example, that have been put out. Sorry, there's a lot to unpack here, but if possible, could you also just comment on how far you think silicon can take us? Do you think it's able to achieve the level of performance to something like a brain, or do you think we will have to move to a different fabric?
There's a lot in those questions that you just asked, Luke. So the Spinnaker project, firstly, is a massively parallel computer which has a communications infrastructure inspired by the very high connectivity that we find in the brain. In many ways, Spinnaker just looks like any high-performance computer, except what we have is very large numbers of very simple processors, and they can connect in ways that can mean that a spike modeled on one processor can be transmitted to 10,000 other processors in biological real time. Chiara's presentation included a picture of a single Spinnaker board in a box. The big machine at Manchester has 1,200 of those boards, incorporating 1 million small ARM processors, and is capable of modeling networks up to the scale of the mouse brain, with quite a lot of simplifying assumptions, of course. Now Spinnaker is one end of the scale, as Chiara said. It's digital. Our neurons and synapses are software models. At the other end of the scale, neuromorphic technologies such as the brain scale system developed at Heidelberg in Germany use analog circuits where the equations that describe those circuits are very close to the equations that describe the behavior of biological neurons. And in between are the sort of hardware, non-programmable, but highly configurable digital platforms such as the IBM True North and the Intel Loihi. All of these use conventional CMOS process technologies. These are the technologies that are in mass production today, building chips such as the ones in your mobile phone, and they're very well developed and in high volume production. Another side of neuromorphics involves the development of new device technologies. These come with strange names such as memristors and RRAM and skirmions and strange things like that. These are all attempts to develop different devices from those used on standard CMOS chips. And some of those devices do look highly applicable to neuromorphics, although they're further down the road than the current systems which are based on standard CMOS.
Okay, thanks for that. That's a very diverse landscape. And if you don't mind, I'd like to bring in Huaqiang and ask a comment regarding AI. We've already had some audience comments actually related to this. So as I mentioned in the introduction, you're working on the hardware for AI and potentially AGI. So the question is, there's been a lot of discussion at this at CogX, but how do you think neuromorphic computing will impact AI?
Well, yeah, thanks, Luke. So I do think, so my background is work on hardware. I actually use a new device to implement neuromorphic computing. Particularly, just as Steve mentioned, I use the RRAM as a fundamental device to do the computing. So the element can do computing and also memory. So they are co-localized together. Actually, it's very interesting. I have done this work for like more than 5 years. So all the results actually is better than the simulation results. The accuracy, the system accuracy. So the system actually quite robust to tolerate some individual device defects or non-ideal factors. So in my opinion, I think neuromorphic with AI, they actually neuromorphic computing is very good for AI because AI, the algorithm is very large and have lots of weights and lots of computing. And those computing need lots of computing power, and which current CMOS chip cannot support. So with the neuromorphic computing, either we use the in-memory computing in memory or use spiking, actually can reduce the energy consumption dramatically. So that's going to support AI technology and to really go to applications. So that's my opinion.
So you think that the CMOS implementations of the neuromorphic computing are going to have inherent limitations then? And that
in my opinion, I think if CMOS have two parts, one is just digital with that, another one with the spiking. So spiking certainly have some advantage to save energy, but still spiking with this computing in memory, the new device together, I think could make this computing more powerful.
Okay, sorry, Chiara, I would like to go back to you because we've now discussed these kinds of spiking architectures and also the digital. And in your presentation, you mentioned that neuromorphic computing is trying to understand the key computational principles of the brain. So do you actually think that future developments in this field are going to rely on a deeper understanding of the brain? Or do you think that neuromorphic computing could actually provide insights itself into the human brain?
I think it's both. Mainly, we use neuroscience research to develop new circuits that better capture the computational principles of neurons and brains. But it's also true the way around. We have similar technological constraints. So the brain cannot be very large. It cannot consume so much power. It cannot, the wiring is very complex. So developing technology that can kind of work in the same way with the same physical constraints can give us insights on how the brain can work. For example, some computational modeling of the brain use synapses with infinite and analog values for the weight, or even negative values. Well, these are not implementable in hardware, and it's not possible that the brain works like that. So we can understand some of the limitations and how the brain solved these limitations, and there's a continuous interplay between the two.
Yeah, I would like to ask a little bit more about this interplay, because neuromorphic technologies requires people to come from all sorts of different communities. Not just computer science and electronics, but neuroscience, physics, material science. How well do you think that is currently happening, these kind of cross-community interactions? And are we training the sorts of people that have the expertise to actually to work in this area going forward?
It's a difficult thing to do, to put together very different communities that have very different language as well. But there are examples that work very well in terms of collaboration between PIs that collaborate to understand the brain. People doing more experiments in computational neuroscience, and engineers like us that try to develop these technologies. In terms of training, it's a very good question. We have now, for example, a big European training network where we put together people doing experiments with wetware, people recording from mechanoreceptors of the skin to understand how the tactile signal in the skin is encoded. And we work together with students that work on the electronic design of how this type of encoding can be implemented in silicon to endow the robots with neuromorphic tactile sensors, and up to the application level where we have prosthetic devices and robots. So I think this type of training networks, they can put together different expertise and train the students, PhD students, to work together from very different domains. It's a very good exercise, and we are also learning a lot from that.
Yeah, that's great to hear, and they sound like very interesting networks. So I'd like to ask a similar question to you, Steve, which is from the kind of chip designer side. How is it that you actually, what are the key kind of drivers for you when you're doing the chip architectures, and what are your interactions with the different communities? I imagine you have different demands depending on who it is that you're talking to. So what's that process like?
Yeah, I mean, the core skill in my research group is the design of microchips. That's where we come from. And Spinnaker was very deliberately designed to contribute to brain science. So it was not intended to be an efficient delivery platform for applications of neuromorphics. It was intended to be a research platform for advancing our understanding of how the brain works. And we were fortunate in that just as we had the machine coming together, the EU flagship Human Brain Project started, and we joined it at the outset. And within the HBP, we're in touch with a huge community of European researchers from medicine to wet neuroscience, to theoretical neuroscience, computational neuroscience, people who model brains in high-performance computers and so on. So we're part of a very rich trans-European community. When we all get together in the annual summit, there are something like 500-600 people all coming together with interests in different aspects of brain science. So it's highly multidisciplinary, And not all those disciplines are represented in my group in Manchester, but we have connections with all those disciplines across Europe.
Okay, thank you for that. So we've just heard about some interesting European projects. So Huaqiang, I'd like to go to you. I know that your center itself has people from quite diverse backgrounds inside. So maybe if you can just give a little bit of an introduction as to why you did this, and perhaps expand on the broader neuromorphic initiatives in China, if you can.
Okay. Yeah, I think, look, just give a very good question. So basically, let me quickly briefly introduce the center. This center brings the different faculties from different departments, including bioscience, including computer science, including math, and also certainly from electronics, and also from physics, and also materials. So we actually have a very broad faculty coverage. So I like to I would like to talk about this course field. It's very, very important. Recently, we did a work which is I feel very excited. Basically, we have a device. It's not a non-volatile device. It's a volatile device. So we feel it's maybe just a switch. And then I showed this result to a bio faculty. He said this device is actually like a dendrite. In our brain, we not only neural synapse also have dendrite. So he said that this device performs like a dendrite. So in our neural network, we always believe, we have the dendrite just capable to transfer signal from the synapse to the neuron, to soma. But actually in our brain, the dendrite could filtering some signals. Actually, that's one important reason to make the energy more efficient. Also, that's also could be the origin from the attention of our brain. So actually, then we develop this dendrite device into a network. So actually, can achieve another 20 times higher energy efficiency. So I think this course field is very, very important, and that's give us lots of insights on how to make our computing more efficient. And so for the neuromorphic computing initiative in China, I think it's very hot in China right now because with the Moore's law slowing down, and with the AI requires more computing power, and the people are looking for some new approaches from new device, also from new architecture, and also new computing principle to try to solve this computing power requirements. So there are lots of research groups are covering from material to the chip and also to system. So this is very active right now.
So we mentioned, we're discussing that it requires people to come from so many different areas, and the architectures in some respects are very different to conventional architectures. But Steve, maybe if I can go back to you, do you think that neuromorphic computing will develop in countries that have strong semiconductor kind of like bases, the places where the semiconductor industries are strong? Do you think it's natural to come out of there? Like the chips that we're already seeing are perhaps from places that we would recognize? Or do you think that neuromorphic computing going forward is a real opportunity for for nations that are perhaps not so well established in chip manufacturing, such as the UK? Do you think there are opportunities there?
I think there are opportunities for everybody because there's still a lot of open questions and questions from the brain science. We still fundamentally do not understand the principles of operation of information processing in the brain. And that's really vital, and it's a roadblock for all forms of AI, including neuromorphics. But then there are the theories that emerge from that, and developing theories of brain operation is something that can be performed by researchers pretty much anywhere. And there are centers of strength in Europe and other places, through to architecting the chips and then manufacturing the chips themselves. And if you look at the semiconductor industry, the centers of excellence in chip design are not the same as the centers of excellence in chip manufacture. So there are many excellent companies in the UK and in Europe who are designing chips that are then being manufactured in foundries in places such as Taiwan. So I think that there's opportunities for anybody involved in anywhere down this hierarchy of research activities to get involved. And it's still a hugely multidisciplinary challenge. And so the more people that get involved and the more ideas that come into it, the better, in my view.
Sorry, Steve, I just wonder, you just said that that we fundamentally do not understand the workings of the brain, which obviously is very much true, but that you also think this is essential, which I found somewhat disturbing. So do you think this is the most critical issue at the moment for neuromorphic computing, or do you think there's still lots that can be done even with current understanding with algorithms and hardware? And
I think we can make progress with what we already know, and what we know is advancing significantly. And we probably don't need anything approaching a complete understanding of the brain in order to make very significant progress in applications of neuromorphics and AI. But the more we understand the brain, the more we can take ideas from biology across into engineered systems. And I do think that understanding the brain is a fundamental roadblock to artificial general intelligence, but I see that as being a long way down the road from where we are now.
Okay, and Chiara, as a user of some of these new chips, can you maybe just comment on what it's like to actually interact with these new hardware? And presumably there are, the algorithms and software are all being tailor-made at the moment, and how you think going forwards, maybe mass adoption will potentially be rolled out.
Yeah, so you use the right way, that is tailor-made. So there's a huge effort from the groups that are developing this type of hardware to develop tools for other researchers to be able to use these systems. And this is, I think, one of the major problems that hinders the mass adoption of these devices, because it's not like you have the traditional computer. You just have a programming language, and you deploy it very easily. You need to first understand how to make the networks, and then understand how to program them on the hardware. There's a lot of progress from the different groups in this respect, but still it requires also to know how to use the neural network and spiky neural networks to perform computation.
So you said that you mentioned in the presentation that robotics and health monitoring you think will be some of the earliest kind of large-scale implementations. What do you think the key challenges are towards that adoption?
Changing the way people working in robotics think about sensory system is something that is required. It's difficult for a person who always did computer vision with frames to move towards not having frames and think about how to solve the computer vision problem with a completely different type of input. This is the major challenge that we are facing, and there's again progress also there. There's a few groups. We have not only humanoid robotics now, but also people working with drones, so with very fast navigation systems that can really take advantage of the low latency and low computational demand of vision done with event-driven vision sensors. And I think it's a matter of changing the perspective on how to develop computation with these systems.
Yeah, that sounds like some of it is a kind of societal and kind of a mindset issue, and that there are already capabilities out there that are currently being underutilized. So maybe from the hardware side, if I can go to you, either Steve or Huaqiang, how do you try to get people adopting or interested in your technologies that you're developing?
Shall I go first on this? I think, the Human Brain Project has created a great environment, and the Spinnaker machine is openly available under the auspices of the Human Brain Project. And there are about 100 copies of Spinnaker boards around the world as well. So we have a sort of global distribution of research users. And within the Human Brain Project, there are the software frameworks built in order to enable people to access the machine freely from wherever they are. We run large numbers of jobs for external users. And that's all moving forward within the Human Brain Project under what's called the eBrains infrastructure in the next 3-year phase.
Sorry, can I just jump in on that? So you said that people can actually access the hardware from the cloud, and you have a good user base that is now building up for this architecture.
Yes. Yes, it's openly available. You have to join the HPP community and apply to use the Neuromorphic platform, but there's no cost involved, and there's no real sort of test of what you're going to do with it. So in that sense, it's an openly available platform.
Are we seeing universities or institutes maybe making use of this for the training of the younger scientists?
I think it's primarily used in research. So I think most of our users will be PhD students or academics. I'm not aware that it's being used for training undergraduates at this stage, but that's always a possibility. We have a very easy to use interface through Jupyter notebooks, which are well used in undergraduate education, and you can access Spinnaker and you can couple it to a virtual neurorobotics environment. So we see robotics as a very important embodiment of neuromorphic systems, and Chiara is doing it with physical robots, but also in the HPP there are virtual robots, and you can remotely build a neural network, couple it to a robot, and see what it does through the fairly easy to use Jupyter interface.
Okay, sorry, Huaqiang?
Okay, yeah. So for my case, it's quite different with Steve. So Steve is making a big computing facility to stimulate the brain. For my case, I want to actually make a new chip which can be used in, say, robots or in the smartphones. So in this case, actually, what I'm trying to do is actually from two parts. One is right now I'm trying to collaborate with some companies. They are very interested in this computing in memory technology, because they potentially can make a very low power training chip. All the training right now is done by GPU, which is very high power consumption. It's impossible to be introduced into the smartphone. But with this computing in memory, potentially we can do that. So this is one way. Secondly, from the technology chain, because the bottom is it is analog computing, so it's very different with digital computing. In that case, we actually also try to develop a compiler, so make all the programmer easier, and so the compiler can help to change it from the digital to our suitable RM computing. So this kind of two approaches we are working with.
Okay, that's very interesting. So Chiara mentioned in her presentation that this von Neumann bottleneck with memory and computing is a big issue. So do you think that the adoption of neuromorphic might even be quite gradual rather than kind of revolutionary, that it might be that the memory and compute just gets a bit closer together and closer, and then eventually there's more of a kind of neuromorphic architecture that's evolving?
Well, from my opinion, I think this neuromorphic is not replacing the digital computing. They probably will be together to make the whole system be more intelligent. So some tasks, maybe some application is better with the existing digital computing, but some intelligent work, the task is actually like AI and some other applications is good for this computing in memory with analog device and analog computing. So this is my opinion. This is also the way I'm trying to work the system. So as you may remember, I try to develop a whole system right now. So in that system, I hope I have both digital, also this is computing in memory. So that's what I'm working on.
Okay, before I wrap up, I just want to check. Do you have any questions for each other before we move into the Q&A?
Not at this stage.
Okay, well, yeah, with that, I'm going to attempt to try to wrap up, which is that it's a super exciting time for neuromorphic computing. We're still dependent on how much insight we have into the, understanding the workings of the brain. But neuromorphic computing already is showing its capabilities for areas such as robotics, such as with event-driven kind of sensing. And it's very likely that we'll see adoption in robotics and in healthcare in the future, although the timescales maybe are not so near future. There is a lot of different hardware architectures that are being put out there now that are very exciting, predominantly silicon-based at the moment. but it's possible that we will move beyond silicon to other fabrics in the quest to try to develop hardware that can compute as efficiently and as well as the human brain. So I'd like to thank all of the speakers from this session and all of the participants for dialing in. And please join us for the Q&A session that starts at 11 o'clock. So thank you very much.
Want access to more CogX videos? Subscribe now for free at cogx.co.